Hello and welcome to Additional Maths Lesson 35 with Mr. Barrow. Today we're going to be looking at estimating areas under curves, specifically the trapezium rule. In Lesson 34 we looked at splitting the area under curves into rectangles. Today we're going to be looking at a better estimate by splitting the area under curves into trapezia. Before we have a go at this question here, we're going to look at what the trapezium rule actually is. In the exam, you will be given the trapezium rule. You'll be given a formula, and here's what it looks like. And at the moment, if this is the first time you've met it, it'll look a little bit complicated. What does it all mean? What are all these symbols? What do these letters indicate? I'm going to go through and explain where all of this fits in, what all of this means. Okay? So I will come back to this formula at the end once I've explained where it comes from. So let's look at splitting the area under a curve. So here's a curve y equals some function of x. If I split the area up into one trapezium, so that means creating one line which joins the points where those different values meet the curve. So split the area between x0 and x1, those two x values. So I want to make an estimate of the area under the curve, the blue area. And this red area here is an estimate of that. It's an underestimate because the curve curves above it, but it is an estimate. Okay? In order to find the area of a trapezium, hopefully at some point you've learned that the area of a trapezium is half the sum of the parallel sides times the distance between them. That's how you calculate the area of a trapezium. And that's what we're going to be using to find the area of this trapezium. A trapezium is a four-sided shape where one pair of sides are parallel. So the parallel sides we have are these left and right sides of this trapezium. You're probably used to seeing a trapezium where the parallel sides are the top and bottom, but it doesn't really matter where they are as long as you have one pair of parallel sides. So, for the area, we need half the sum of the parallel sides times the distance between them. The area under the curve is not equal to that. It's approximately equal to that. So I'm going to put approximately equal there. So half times the sum of the parallel sides. So the sum of the parallel sides, okay. The parallel sides are those green lines on the left and the right of my trapezium. I'm going to call those y0 and y1. y0 is the corresponding y value for the x-coordinate x0. That is the height of the curve when I have the x-coordinate x0. And y1 is the height of the curve when I have the x-coordinate x1. I like using x0 as my first x-coordinate because then it allows me to go up to x subscript the number of the trapezia that I'm using. So if I'm using one trapezium, I end with x1. Okay, and you'll see with further ones what it looks like when I have 2, 3, etc. trapezia. So, half the sum of the parallel sides. The sum of the parallel sides is y0 plus y1, multiplied by the distance between the two parallel sides. The distance between them is x1 take away x0. It is this distance here. I'm going to call that distance h. In every question, we're going to use h as the width of each trapezia. Okay? The distance between the two parallel sides. So half of y0 plus y1 times h. And that is how to calculate the area of that trapezium, which is an estimate for the area under that curve. The way it's written usually, though, is half h brackets y0 plus y1. Okay, so now let's have a look at what it would look like if I had two trapezia. One trapezium is very simple. I wouldn't use the trapezium rule for it. I would just calculate half times the distance between them times the sum of the two parallel sides. But let's develop a little bit more knowledge by using two trapezia and then three trapezia and see where it gets to if I wanted to use n trapezia for my trapezium rule. So if I had two trapezia, so I split this area under that curve, so this is the same area, it's the same curve, y equals f of x. Instead of one trapezium, if I split it into two trapezia, I have now three x coordinates which split that area. x0, x1, x2. So look, I end up with x2, which means I'm using two trapezia. And the corresponding y values are y0, y1, and y2. Okay? Now I'm going to introduce a little bit more sophistication. I'm going to introduce some notation which we're going to start using. That notation is this here. This notation is the notation we use to find the area under curves. The symbol, which is an elongated S, is the integral sign. And it says the integral between x0 and x2 of y with respect to x dx. And that just means I want to find the area under the curve y equals f of x. As we move along in the x direction, as we go this way in the x direction, what is the area between these two x values, x0 and x2? Okay, and that is approximately equal to the area of the two trapezia added together. It's not exactly equal to it. We're just estimating it using the area of trapezia. So you're going to use this symbol a lot over the coming lessons, especially when we're going to calculus where we find the exact value of the area. But you're going to see that in the formula, so I thought I'd just show it to you first. So if I wanted to find the area of A, the area of A is half times the sum of the parallel sides times the distance between them. I'm going to do the distance between them first. So as before, I'm going to call that h. H is that distance between the two parallel sides. So half of h times y0 plus y1. So that's the first trapezium. That's A. And then if I add the second one, that will again be half h multiplied by, this time, y1 plus y2. So those are the two parallel sides for the second trapezium. Okay, I could simplify that. I could factorize that and write it like this. I could take a factor of a half h from both of those expressions. So that would become half h multiplied by y0 and y1 plus y1 and y2. There's a simpler way of writing that, and I could rewrite the y1 and y1 as two y1s. Now you'll find that if you have more than one trapezium, you will get parallel sides which are used in two different trapezia. So A and B have an overlapping y value of y1. y1 is used in both trapezium A and trapezium B, so I need two of those y1s. But I'll only ever need one of the end y values, y0 and y2, because they're not used in overlapping trapezia. When I say overlapping, I don't mean they actually overlap. I mean they are connected, okay? They meet at a specific value. Okay, so that's for two trapezia. Let's get a little bit more sophisticated. Let's look at three trapezia. So this time, again, I could split the area up into three different trapezia, A, B, and C. So the area under the curve y, as we move from x0 all the way to x3, so that's what this formula says, is equal to the sum of A plus B plus C, or is approximately equal to that. So, as before, h the distance between the parallel sides is that value, okay? And we always split the area up into trapezia with the same width, okay, the same distance between the parallel sides. So A would be half h times by y0 plus y1. B would be half h times y1 plus y2. And C would be half h times y2 plus y3. And I could factorize that again and simplify it. And that would turn into half h multiplied by y0 is only used once, y3 is only used once. I'm going to put those together, y0 and y3. Those are the end y values. The other ones, there are two of. There are two y1s, there are two y2s. So there's two lots of y1 and y2. So all other y values you will have two of. So that's the formula with 3. Now we'll move on to n different trapezia, which then creates our formula as it's seen in the formula book at the front of the exam. Okay, so this time I split the area up into A and B and C and D, etc., all the way up to the end. So there are n different trapezia. I start with an x value of x0, then x1, x2, etc., all the way up to xn. So I end with the number of trapezia I have as my final subscript of x. So that means, remember, that we have n plus 1 different x values. Because that when we had one trapezium, we had 2 x values. When we had 2 trapezia, we had 3 x values, etc. And similarly, y0 goes up to yn. So we have n plus 1 different y values. So the first trapezium would be half of the distance between the parallel sides, so h, which is this distance here, and it's the same for each one. All of these are h apart. So that half of the distance between the parallel sides times the sum of the parallel sides. So first one would be y0 and y1. The second one would be y1 and y2, etc., all the way up to yn minus 2 plus yn minus 1 for the penultimate one. And then the final trapezium would be yn minus 1 added to yn as the sum of the parallel sides. And then if I factorized half h out of that, then that would become half h, and then a big bracket. There's only a single y0 and a single yn, so I'll put those first, y0 and yn. And then there are 2 of every other y value, so 2 lots of y1 plus y2 plus y3 all the way up to plus yn minus 1. And that is the formula if you're using n different trapezia. And that corresponds with the formula they give you. So here, this formula here, which we have understood and created, where we're doing half of the distance between the different parallel sides multiplied by a single y value for the end y values, so y0 and yn, and then 2 of every other one, matches up exactly with this, which is what you're given. So you don't need to remember this, but you need to know how to use it and what those different symbols mean. So here, this bit means the area below a curve, y equals f of x, between a and b, is approximately equal to, so that's approximately, is not equal to, it's approximately equal to the sum of all the n trapezia, which is that calculation, and where h is equal to b minus a over n. Now, here they're using a and b rather than x0 and xn, but it's just replacing the first x value and the last x value with a and b. So if I had the first x value is a, the final x value is b. So I'm finding the area under the curve y equals f of x between a and b. And I'm splitting up into n different trapezia, then to find h, which is the width of each individual trapezia, I do this distance here, which is b minus a, and then I divide it by n, and that will give me h. Okay, so let's look at this in action with an example. Okay, if I can find the example. Here it is. So, use the trapezium rule with 4 trapezia to find an estimate for the area bounded by the curve y equals 2 to the power of x plus 5 and the lines x equals 1 and x equals 3 and the x-axis. Okay, as always, it's always good to visualize the problem. So, sketch the function you want to find the area under. Okay, y equals 2 to the power of x plus 5. When x is 0, y will equal 2 to the power of 0, which is 1, plus 5, which is 6. So it'll go through the y-axis at 6. And then it'll increase exponentially, so it'll have some increase, something like that. Okay? And I want to find the area between that curve, y equals 2 to the power of x plus 5, the lines x equals 1 and x equals 3. So I'm trying to find an estimate for the area there that I've shaded in green. Okay, and we want to split it into 4 different trapezia. If I split it into one trapezium, the value of h would be 2, because these are 2 apart. In the formula, remember that h is equal to b minus a divided by n. Here, b is 3, a is 1, and n is 4 because we are using 4 trapezia. So our value of h in this question is 2, which is the distance there, divided by 4, which is 0.5. So each trapezium is 0.5 apart, which makes sense because if I want to split the area between x is 1 and x is 3 into 4 different sections, I would go 1, 1.5, 2, 2.5, and 3. And that would then split the area into 4 different sections, each the same width apart, each 0.5 apart. So at this point, a good idea is to write a little table of values that you're going to be using in the question. So x and y values. So what is my x0 value? That's 1. Next one is going to be 1.5, then 2, 2.5, and 3. And then write down your corresponding y values. The y values for these are 7. I'm going to write them in green. 7. When x is 1.5, the y value is about 7.8-ish. When x is 2, we have 9, because we have 2 squared plus 5, so that's 4 plus 5 is 9. When x is 2.5, we have 10.6 approximately. And when x is 3, we have 13 exactly, because 2 to the power of 3 is 8, plus 5 is 13. And then once we have our values, we can just simply substitute them into the formula. So the area is approximately equal to half times h, which is 0.5, times the end y values first. So one of those, 7 and 13, and then 2 lots of each individual y value between the end y values. So that's 7.8 ... plus 9 plus 10.6 ... And that calculation will give you the area of the 4 trapezia, which is an approximation for the area under the curve. And that will equal 18 0.74264 ... But since I'm giving an estimate, I shouldn't be that accurate with this at all. Okay, so 18.7 to 3 significant figures is my area that I've created using the trapezium. This is an overestimate of the actual area because my trapezium, since this curve is curving upwards, the trapezia, if I draw straight lines, will all be above the curve. The curve will be below the trapezia. So this here is an overestimate of my area. Okay, because the trapezia rest above the curve, which is curving below it. So that's how to do it. Firstly, find the value of h, which is how wide apart each trapezium is. And then do a table of values, find all the y values that you need. And then you're going to substitute them into the formula where you use one of the end y values and two of each of the others, two of those. Okay, have a go at this question here. Use the trapezium rule with 3 trapezia to find an estimate for the area bounded by the curve y equals root x, the lines x equals 16 and x equals 25, and the x-axis. So pause at this moment, have a go yourself, visualize the problem, make sure you do a drawing showing what it will look like, and see how accurate you can be. Okay, there is one answer to this. Even though it's an estimate, there is one answer that is correct for the estimate. Okay, because of what the question has asked you to find. See if you can get the same answer that I do. Okay, so the answer to this is as follows. Your visualization should look something like this. So the y equals root x is curving down. The x values are 16, 19, 22, and 25 because that will then split up the region into 3 trapezia. Since 16 and 25 are 9 apart and we want 3 trapezia, each width is going to be 3 apart. So 16, 19, 22, and 25. And so the y values are 4, which is the square root of 16. The next one is root 19. Next one is root 22, and the next one's 5. And if we substitute them into the formula, we should get 40.6 to 3 significant figures. And this is an underestimate since the curve curves above the trapezia. But it should be a pretty good estimate. Okay, what you should do now is you should practice exercise 13.6 from the textbook. Practice it until you feel confident using this formula and understanding how to do so fluently, accurately, and quickly. In the next lesson, we're going to be moving on to something called calculus, which is the very best part of maths. So we're going to be moving away from numerical methods and into exact methods, algebraic methods of calculating gradients of curves and areas under curves without having to resort to estimates. Estimates are all well and good, especially when our algebra falls apart, but it is just lovely doing the algebra and working things out exactly. So I'll see you in the next lesson. Enjoy.